Hello and welcome, friends. My name is Shailesh Agarwal, Executive Director, Building Materials and Technology Promotion Council, Government of India. And today I have with me Mr. Paul Florenai from Australia, and he's one of the founders of 3D Modular Volumetric Precast Concrete Construction and has been successfully delivering structures, buildings, apartments there. Mr. Paul Florenai is key principal of Green Precast Australia Private Limited at Victoria, Australia. The company is the worldwide pioneer of 3D volumetric monolithic concrete modular construction, innovation, and working in several countries. At the outset, I am indeed grateful to you for making yourself available at such a short notice. I welcome you, Mr. Paul Florenai, for this interactive session. Being one of the few experts of 3D volumetric modular construction in the world, we are fortunate and we are really blessed to have you here with us today. I'm going to ask you a few questions about the technology, its features, implementation aspects, etc. We are recording the entire session with the objective that the viewers can understand the various nuances of this innovative system and at the same time decode the prevailing misconceptions about structural and functional performance. So Paul, if you're ready, please explain us in detail about the technology and how it is different than conventional cast in situ RCC frame construction.
Thank you very much for having me, and it's a pleasure. I always enjoy sharing what we've learned over the journey with other people and other people that are interested. Effectively, it's a three-dimensional precast panel. So I think everybody now is familiar with casting 2D precast concrete elements as flat elements that then stand up in position as walls or roofs or the like. We've just taken that one step further and said, let's join the four walls to a typical room with a concrete roof slab, all cast monolithically together in one concrete pour. So it's effectively a giant Lego block. So it uses the same principles as concrete and steel for generations all over the world. It's the same concrete, it's the same steel, albeit just tweaked a little bit to assist us with our particular construction technique. So I think, you're all familiar with culverts where they cast the walls and the ceiling of a culvert. We've now put a wall on each end of that culvert to make it a completely enclosed room, which then stacks up like Lego blocks. It's a little bit more difficult to transport, but in terms of speed of construction, in terms of monolithic construction, in terms of engineering, it just sort of assists with so many other elements of our building cycle that we think it's got some real advantages. We think it's the way of the future. It allows us to then do some more fit out of the room structure in the factory and in a controlled environment so that you can paint, you can put windows in. But the principles are very, very similar to conventional precast that's been used all over the world in every continent, in every type of weather pattern, and in every type of seismic zone. It's just taking it to the next level.
Okay. Now let me ask you a few questions. First of all, it comes to mind why one should adopt this innovative system for building construction.
What was that? Why did we do it?
Why one should adopt this 3D volumetric construction for building construction?
Why do we?
Yes. Why do we? Yes.
Look, construction is very dangerous in a lot of formats. There's a lot of risks associated with building vertically. When you have a monolithic structure, it's very stable and it doesn't require props. It doesn't require brackets. And as you know, in Australia and a lot of the Western world, our cost of labour and our requirements on site for occupational health and safety are quite high. And so we looked at doing something, especially for remote areas, especially where speed of construction is so important. We could control the fit out process much more succinctly by doing more and more in the factory, in a casting yard sense. So rather than wait to get to site where you're at the mercy of the weather, at the mercy of suppliers, of contractors, of a whole range of other activities, we can control as much as we possibly can in a factory environment, and that's where all modular type construction wants to head to, bringing manufacturing processes that we're familiar with in cars and in joinery and so many other parts of our society, bringing that to the full scale of construction is really where we're trying to get to.
Yeah. Are there any limitations of these systems?
Yeah, of course, there's many limitations. The biggest single limitation is probably transport and logistics. Because you're trying to make larger elements and larger finished rooms, then they have to be transported from their manufacturing location to their in situ location. So the infrastructure, the road infrastructure, the permits, the widths of travel, the weight of the units, all of those things present us with some challenges. And each country is different, and even in regions within countries are different because of the permit systems and what's allowed to go on the road. So in an ideal world, and India is very, very unique because you have such large volume projects, it's still very possible to put a manufacturing yard within your project site. Whereas in Australia, we don't really have that volume of project very often. So we have to then look at ways to transport across vast distances completed modular structures. So the transport is one of the biggest limitations. And secondly, I would say the funding models. The funding models are, again, a little bit different all over the world, but in particular, when you're doing smaller scale projects, people and banks don't like to fund construction until it's on the construction site for the obvious risks associated with funding something that they don't have some sort of mortgage over or some sort of legal right to. If they're funding something externally, then it's very hard for them to get security over that product that is manufactured off-site. So we find in Australia in particular, the funding models around construction present us with challenges of manufacturing too much off-site.
Okay. My next question is, as you know, India is a vast country having different geoclimatic zones and prone to multi-hazards like earthquakes, floods, windstorms, cyclones. Do you really think 3D modular volumetric construction has future in India and can be adopted as technology for future construction?
Absolutely. If you look at India's climatic range of climates, it's no different to individually any other place on the planet. Iran, seismic zone 4, the system works. If you look at monsoons, yes, you have huge monsoons, but good precast detailing is been used in Singapore, in Hong Kong for many, many years, generations, and they can solve these detailing issues with good detailing and good design. So heat, in the Middle East, not much more severe than the Middle East. We've manufactured modules in the Middle East. So concrete is used in every corner of the planet, reinforced concrete. So all this is doing is taking a next generation reinforced concrete element and designing the peculiarities to suit the particular environment. If there needs to be weather steps, we can design them in. If there needs to be more connections for seismic, we can design them in. If there needs to be more lateral load restraint, we can design them in. If there needs to be vertical sandwich panels for heat environment, we can design them in. So it's a manufacturing process. It's just using a manufacturing environment to create a reinforced concrete product that suits primarily speed of construction. And the beauty and the best thing about modular construction out of a factory is the repeated quality. So if you have a mold that is built properly in the first place. It's like making a cake. The ingredients may differ, but the cake tin dimensions stay the same every single time you make a cake. It's the same with a module and a mold. If you make a module out of the same mold 500 times, you should have 500 times the exact same dimension. And you're not relying on trades, skills, site supervision to get that wall straight and plumb every time, because it's already predetermined for you in the mold and in the factory. So that's what manufacturing and factory-based construction does. It improves the speed, it improves the quality.
Nice. Next question is, Paul, I know you have been successful in mainstreaming this technology in your country, but tell me, when you started, what was the general perception of engineers and architects about the technologies? Were they really willing to implement? What are the impediments or barriers which we all have to overcome to mainstream it?
Sure. Look, I use the example, the construction industry is a giant behemoth. It represents 10% of GDP in most countries, and it is enormous industry. And it's probably one of the slowest moving industries that we have. If you think about 2,000 years ago, we were using blocks and mortar to make housing. Today, that still exists. But when you have a look how quickly the finance industry and our telecommunications industry has moved, it's exponential compared to the rate of change in construction. So the construction industry is slow to move, but there are so many moving parts and so many different trades in the construction industry. So one of the biggest issues we have is we need the buy-in from the developer or the client to the developer, to the builder, to the designers. Everybody needs to agree we're going to do this. Too often, and where one of our biggest impediments comes from, is that we get a set of already developed working drawings for a particular construction project. And people say to us, quickly, give me a price for modular construction as an alternative. Well, modular construction is based around set sizes, is based around using the strengths of a modular structure and a factory-based repetitious model to give you the outcomes and the improvements. Now, if you have 15 different sized rooms throughout a project, it's very difficult to modularize that. So you really need the designers to buy in at the start. You need the developer to say, yes, I want to build it quicker. You need the client to say, look, this is worth the push and the innovation because I want the long-term durability and the quality. So the entire team needs to kind of buy into the modular process at an early stage, or at least design for it such that it can be allowed if the commercials say that it does work. So too often we get involved too late in the piece, and that's a very big impediment to what we're doing. The other thing that I think we, again, we're very apathetic in the construction industry is that we always revert back to what we know and what we've done before. So oftentimes you'll get the engineer who will design the same footing that he used on the last building because it worked and then nothing happened and nothing went wrong. So therefore, let's just get those details and use that. And I have this argument and discussion many times with engineers and architects and say, well, let's challenge the reasons why we're doing things. And let's go back to first principles. Why are our boundary walls 190 millimeter thick? They don't need to be. Well, that's what we've always done. Why have we always done that? Because ASTM, British standards, Australian standards can show you that 150 mil wall or 140 mil wall can give you a 3-hour fire rating on the boundary. So why do we go to a 190 millimeter wall? Because that's the size that our block work always was. And that's what we've always done. Well, let's go back and challenge some of those things. And let's work at the first principle side of it rather than because it's all what we've always done. And I find that's a big challenge too, is that nobody likes to be the maverick. Nobody likes to be the first person to put their hand up and say, yes, let's do something different. Everybody is looking for the risk averse, somebody else to take the risk and then we'll follow. That's also very hard to overcome.
Wonderfully answered. Wonderfully answered. My next question is about the structural performance. You know, often we encounter this question that what is the structural performance of buildings being done with this technology in comparison with conventional cast-in-place RCC construction?
Look, it's a good question. Again, this is where our engineers have to think about the principles of what we're trying to do. What is the strongest, most stable structure in our natural environment around us each and every day? And if you have a look, go back to first principles again, it's a honeycomb, it's a beehive honeycomb, and an ant's nest. Have you seen an ant's nest, how intricate it is? And it's made up of series of cells that share common walls. And what you have is a series of shear walls working horizontally, vertically, and in all directions. It's an exceptionally stable structure. And so, you know, when you look at a space frame that spans 250 meters over a stadium roof, what is it? It's a giant space frame that has elements working in all different directions. But what we do conventionally is that we build a column with a capital head on the column, and then we have beams coming off of that, and all the load from the whole floor's got to come down one column. And if we have a blade wall there, then a blade wall can share a lot more load, and especially you have 2 intersecting blade walls, and then 3 intersecting blade walls and 4 intersecting blade walls can take an enormous amount of load, not only vertically, but in shear, when you have, you know, shear walls and seismic activity. It's an infinitely better solution. Again, go back to what's one of the strongest natural structures in our natural environment, an ant's nest. You try and push an ant's nest over one of those giant ant's nests. It's very difficult to do because it uses a lot of little elements contributing a little bit rather than one big element contributing a lot. So, you know, again, engineers, you need to get out of the box and you need to think, use your brain. And then we've got some fantastic programs now, finite element packages that were not around 20 years ago. You can model this stuff now. You can run it through sophisticated programs, and it shows you how you can distribute the load paths of an entire building very, very uniformly out and through many small elements. So, you know, people say this to me all the time. Well, okay, what do we do conventionally? So we look at the soil, and then what we try and do is we design an infinitely stiff raft slab to take all the load that nothing ever moves at a very thin element, a thin crust. And then we put brickwork on top of that, which is a brittle structure with lots of joints. And we don't want any of those joints to move or crack, so that the slab on ground becomes very, very stiff element. So if you take modular structures above that and you give them depth, the depth of the walls actually give it the infinite strength. It's a space frame above the ground. And again, take another little example. If you take a pontoon is an element that sits on water that's got no rigidity below it, right? And the depth of the pontoon is what gives it its rigidity. And you can have the entire pontoon filled with air. So we just got to apply our thinking a bit differently and say, well, okay, I get this. It's a giant pontoon floating on, you know, the soil doesn't have to be that good at all. If we recruit the height of the building to act as a giant matrix of elements that are all working together. So that's a simplistic engineering analogy, but what we often do is just go back to what our old software allowed us to do. And you know, ETABS and you know, I won't name them, but you know, our old software was very, very linear and very, very elemental. What we need to do is look at our more sophisticated softwares, because it will allow us to then develop these new thought processes about how structures should act. And one last thing, and again, I'm really taking off on a structural tangent here, but you know, some of the technology, some of the research coming out of you know, Japan and the seismic zones is that buildings need to be ductile. You know, we make rigid buildings and we submit them to horizontal accelerations, and they're very rigid, so they crack and they break. Now, if a building is ductile and it has a lot of joints strategically placed, it acts as a ductile element. It can absorb the horizontal energy and the horizontal accelerations. So we have a better chance of doing that with individual modular structures that are all linked and tied together, because you, by definition of how we built the thing, we have lots and lots of joints that can absorb lots and lots of more energy. So we just got to apply ourselves a bit differently to the analysis of this, but it does work.
Okay. So next question is about joints and connections, because that is the common question being asked by everyone. So what about joints and connections as you put module over module and little ground shaking, or that is in the event of an earthquake, if a structural integrity and monolithic behavior of joints and connections are not ensured, these modules will fall one over other. So that is the apprehension of engineers and architects all the time whenever we talk about this 3D volumetric construction. So how do we address joints and connections in this system?
Well, it's an extension of what I just said. So
yes,
if you can picture containers on the back of a ship, and you see them in the rough seas, how the containers 6, 7, 8, 9 stacked high. And because there's a little bit of movement at every joint, a row of containers can lean right over and then come back. The connections are rigid, but the joints are allowed to move a little bit. So the movement is at the joints, not within the actual module itself. So, you know, some of those principles can still apply and should apply to what we're doing. So again, ductility in buildings will give them longevity, because you are predetermining where any movement will be. And you are saying, okay, if there is going to be movement, and there will be movement, it will move here and here, and we can predict that. But the element itself stays structurally integral, but we allow them, each element to element, to move slightly between themselves, so that you're controlling where that movement will be, the cracking will be. And we have some fantastic mastics, we have some fantastic materials now, which will more than adequately move with the building if we design it accordingly. And look, precast has been used in Singapore, it's been used in Hong Kong, Malaysia, all the other countries where there is monsoons. There is weather, there's all types of weather sealing, there's all types of weather joining that can be applied, and we can apply those same design principles to vertical and horizontal joints that we see in some of those environments. And window joints is equally important. We can design those things now. We know how they work. You look at Russia, you look at China, you look at India, you look at monsoon areas, the snow countries, they all use precast concrete.
Just to know it further, because just for the sake of listeners, what kind of connections you use? Is it dry connections, bolted connections, or you connect it through bolt, plates welded together, or it's grouting through concrete and dowel works? So can you just elaborate something on connections for the listeners?
Sure. Look, anything that you can use in normal precast panel connections, we adopt in modular. It's just that the modular element has 4 elements working simultaneously. So when you install one traditional 2D precast panel, you treat that in isolation. And so you have to restrain it on top and bottom and sides in accordance with a single element. But when you have a monolithic element, you can reduce the number of connections, because all the walls are interconnected and cast together, so they are considered as one element. And so the number of connections should and will come down. Similarly, also the mass of the unit is quite heavy. It's potentially 4 times heavier than any single element previously. So its own self-weight is enough to stop it from overturning in any wind or cyclonic event. And we can model that. Again, I've modeled these things 4 and 5 levels high, and in the worst cyclonic and tornado conditions, these things, their self-weight alone holds them in position. But yes, some simple connections. So we do use dowel bar and grouting. We do use welded plates if needed. My suggestion is that if we connected everything at the top of each module by a simple fish plate to keep them together at the top, with some allowable movement so that they stay together, but there is some allowable movement. And then we grout the bottoms of them with some either welded connections from internally or some grouted connections. It's a function of how tall the building is, your occupational health and safety plan to show you, yes, you can go outside the building. No, you can't go outside the building. Is it on a boundary wall? Are there intermediate corridor slabs? Are there stair shafts? Are there lift shafts? All of those things come into play, and a clever engineer will sit down and look at all of those elements and come up with a fixing plan that and a connections plan that is, that works. And again, this stuff can be modeled. You can do an entire 3D model. You can subject it to the wind. You can subject it to the earthquake movements, and it'll tell you that you need so much shear force at each level to be restrained. It'll tell you you need so much uplift for it to be restrained. It's just pure engineering, and is nothing that we can't overcome.
Nice. India being a hot and dry climate, India having a hot and dry climate, sometimes the question being asked is, these modules comprise of thin concrete walls. So does thermal comfort compromise in this technology?
It's a good question. It's not such a big issue in India because India is, your building codes don't really insist on a lot of that sort of thing, and you've got quite a temperate climate. Certainly in Australia, where I am now, it's very cold, and we have to insulate either the inside or the outside of the structural element to get our energy rating up. And both of those can be done. What we're looking at, and what we did many years ago in the Middle East, was we cast a vertical insulation core in the external walls, so that we had concrete insulation and then concrete as part of our vertical wall element on the perimeter of a building to provide it the thermal insulation that it needed. So look, I think absolutely we need to insulate concrete. Concrete is fantastic as a thermal mass and as a heat sink, but once it heats up, it takes a long time to cool down, and once it cools down, it takes a long time to heat up. So I prefer to insulate the outside of the building, because that way you're keeping your concrete thermal mass at a very consistent temperature, and it actually acts as part of your heating and cooling system. It's a thermal mass. It's a heat sink that will then help you control your environment very slowly. But if you stop your concrete from getting extremely hot and you stop it from getting extremely cold, it can be of a real benefit to you. But some people like the durability on the outside of the building and want concrete on the outside. And for that reason, they then insulate the inside of the building, which also works. And it's really what's been used probably in most locations around the world. They insulate the inside of buildings.
What is the fire rating of these modules? Fire rating of these?
Whatever you want it to be. So obviously, everybody wants to use less material for the costs. Use less concrete, use less concrete, use less steel. The more concrete you use, the more steel you have to use, because there's a minimum requirement of steel per volume of concrete. So we have engineered it right down to 9 centimeters or 90 millimeter wall sections, which we can show works for our cover, our durability, and our 2-hour fire rating. We show that that can be achieved. And so if it's a 3-hour requirement, well, then we have to thicken the walls, and you can get away with 1 layer of reinforcement. But once you get too thick on your walls, you have to go to a 2nd layer of reinforcement. So it's a function. Is it a boundary wall? Is it a 4-hour fire rated wall? Is it a 3-hour, 2-hour? We have to be specific about that. And we can cast them whatever thickness the project requires.
So Paul, you may say,
meet the rules.
Please go ahead. You want to say something?
No, whatever the codes of the country are, whether they're Indian codes, Australian codes, there are rules that dictate, what the fire rating needs to be on the boundary. And as engineers, we know what concrete does. We know what a 40 MPa concrete panel can achieve at 150 thick. That's been tested time and time and time again. It's the same steel, it's the same concrete, it's the same thickness. It's just cast monolithically with its internal walls at the same time. It's no different. So we know what all those numbers and values are, and we just apply the relevant code requirement to the external wall or the internal wall or the corridor wall as appropriate, and we cast that thickness.
Just a small question. You just said 90 mm wall with 2-hour rating. That is permissible in Australia? 90
Yeah.
mm external wall. Very nice. Very good. Because in India,
It's-
we
this
have
is-
around, yeah.
Yeah, go on, go on. No,
Go
you
ahead,
go.
go ahead. Go ahead, go ahead.
Look, and so look, you know, that's 40 to 50 MPa concrete,
Okay.
which is, you know, megapascals of concrete. It's a very, and it's highly vibrated, and it's off a steel form. So we're not relying on manual labor to make sure there's no pinholes, to make sure the vibration is correct, because it's all factory controlled. So we have a precast panel that its density is assured because we're casting it in a factory. We're highly vibrating it. It's super plasticized, which means it's very, very fluid. It's 40 MPa, which often goes 50 MPa, and it's allowable up to a 2-hour fire rating to have that sort of thickness of wall. Now, if it's on a particular boundary, or if you go too many levels, once you go above 4 levels, then yes, we have to increase our thickness. But sub 4 levels and on a boundary, you know, a 2-hour fire rating, we can achieve that with a 90 millimeter wall.
Next question is about service life of these buildings. What is the service life of these buildings with this technology?
Exactly the same as any concrete structure. It's you know, in fact, on some of my projects, I give a 50 or 100 year structural guarantee. The other thing, which is probably a little bit more topical these days, is very, very possible in the future to remove the modules and relocate them and put them somewhere else.
That's great.
Yeah, there's a little bit of work involved in that, but it's very possible. You don't have to completely destroy the building. Similarly, it's also possible to take a module and crush it down and recycle it, and recycle the concrete and recycle the steel, the same way it is conventional concrete. So look, it's transportable, as in you can move it around. It's recyclable, because you can crush it down and reuse it again, road base, or you know, recycle the steel out of it in the future. So it's the same lifespan, if not even a little bit more, because with conventional construction, you're still relying on the quality of the skills and the skills of the tradesmen on the site to get the reinforcement in exactly the right position, to get it central, so that the durability to the reinforcement is upheld. So in a factory, we have a better chance of getting that right, because we have spaces and we have factory-based manufacturing techniques that increase our quality and get things a little bit more accurate than what you would do every level and every room on a construction site where you're relying on manual labor. So if the process is factory driven and manufacturing driven, then the chance that our reinforcement is central and in exactly the right position for durability is probably a little bit higher. And because our vibration technique is exactly the same every day, and it's done mechanically with mechanical vibrators rather than hand dropped vibrators or somebody manually doing it on each site, then potentially our concrete quality and our compaction is better than what it would be every level and every room on every pour and every site. And you know what it's like on construction sites. Some days it's very hot, some days it's very windy, some days it's very cold and very wet. And some guys aren't really working as hard today. They're not feeling well, their head's in another place. You know, you're relying on all those variable factors. Whereas in a factory environment, you've got a much better chance of controlling quality each and every day.
Yes. My next question, partly you have answered, but let me just again ask it. Being entirely precast concrete construction, how do you justify this technology to be environment friendly and energy efficient?
We probably use less concrete and steel per square meter of construction than conventional forms of construction. Because our elements are thinner and because we have very little wastage, and because it's very much a design-driven process whereby you know, we are designing the efficiency into the thicknesses of the slabs across the entire project. You have, and it's the same mold every day. So when you order a quantity of concrete, you know within less than 1% accuracy, because you can calculate that volume very, very accurately. Whereas, as we know on construction sites, we always order 10% more, and we're often batching our own concrete, so we have in-house control over quantities and mixtures and stuff going into the concrete mix. Whereas on a construction site, you have less control over what's happening. So it is all about that control and the quality of what's going in. Look, concrete has a bad name in construction, and especially in terms of emissions. But what I say to people is concrete's about 10 to 15% cement. The other ingredients are sand, gravel, and water. 85 to 90% of concrete are 3 naturally occurring products that are found in every quarry pit anywhere in the world. So 15%, 10 to 15%. If you add fly ash and some other recyclable materials, you're talking, 10 to 15%. So cement, yes, is a bad element, and it's a high embodied energy, and it takes a lot of energy to produce cement, definitely. But it can be relocated, it can be recycled, crushed down in the future, and move and completely crushed and removed. And we use less concrete and steel per square meter of construction than fatter, bigger elements, because we've engineered it down to 9 centimeter walls. And all the elements work together more efficiently than individual elements.
Nicely answered. Do you have fly ash in Australia?
Oh, yeah.
Oh,
yeah.
So you have thermal power plants. Power plants. Okay.
Yeah, not many, but we have some.
Okay. Because
we've got lots of coal here.
Yeah. Because we have majority of power is generated through thermal power station in India.
Yeah, right.
Yeah. Okay. My next question is, how do we carry out maintenance of services, that is water lines, electrical cables, sanitary installation, sewerage, etc., once the building is put to use? Do you train people or have SOPs, or it is as conventional as in precast concrete construction conventional?
Very similar to precast concrete construction. It's a little bit more design input. Again, the designers need to get their head around accessibility. Oftentimes we design shaft risers in certain locations where we centralize our services, which is smart design. It's good design for any type of building, not only precast or modular, any type of building. You should have centralized services and shafts to access services. We do cast our electrical conduits into the structure so that potentially, you pull a wire out, you thread another wire through. There's already a predetermined conduit and a wall box cast into the modular element so that you can replace it. It does make it a little bit harder for the future if you want to retrofit, but no different to if you're retrofitting in situ concrete walls. Yes, you might have to chase a bit of concrete in, but that's where, again, in the design process, we probably need to be a little bit more generous with our provisions for services. And the designers need to think about, okay, what's going to happen in the future? Do we need a Wi-Fi repeater in each room? Do we need, high-speed Cat5 cabling in every room? Will we need maybe, different services for our plumbing and our mechanical ventilation services? Maybe just think about the future. Very, very easy to make provisions up front. If you can make some allowances, it would certainly make the future a lot easier, because no one knows where the future is going to be. And look, if we needed to put a false wall in front of the precast concrete wall to add more services, that's also possible in the future. Yes, you'll lose some space in your apartment or in your dwelling, but again, who can predict the future? So we can make some provisions, definitely. So for instance, what I do in Australia is that I make allowances for a double power point on every single wall in every room.
Okay.
Because there's never enough power points in any room.
Yes, correct.
So if you say, okay, on every wall in every room there's a power point, well, that's providing for the future. If you don't use it now, we can put a blank cover on it, but we have the conduit, it's already pre-prepared, it's there. In the future, you can put another wire through, because we have said, okay, I have teenage children, there's never enough power points in their room. The stereo, the phone, the iPad, this, that, is always need for more power points. If you put 5 in, they want 6. If you put 6 in, they want 10.
That's a good solution. Really. My next question is, because this is a new thing, a new technology, and in India, we are always driven by, codes, design aids and all. So tell me something about what codes, design aids and softwares you use to design and construct these buildings and modules.
as I mentioned at the outset, there's lots of good technology now and sophisticated software that you can model. And a lot of engineering companies are going more and more towards finite element analysis. And there's some fantastic programs out there that will and there would be at least 10, if not 20. So what we're doing now is with these sophisticated computer programs is that we are breaking down buildings into more finite elements and seeing how they all work together and giving them all separate properties, because we have the computing power to do that now, and the computer obviously helps us immensely. So it's becoming easier and easier to do. Each and every code in every country is what they call a deemed to satisfy code. It says, if you put this much steel in, if you do that much, then we will say that's okay. But every single code in the world that I'm familiar with says this is deemed to satisfy, and it's a conservative engineering principle of how we do things. And we know that it kind of works. However, if you and your peers as professional engineers and architects want to design something from first principles and show that it can work from good engineering principles, then we will also accept that. It's just that most people adopt the code-based approach to design because that's the conservative model. But every code allows you to do thorough engineering analysis. And so that's, I think, where finite element analysis came from and is more advantageous, because we can show with sophisticated software that is very conservative, and by doing it a different way, it works too. And then the next step would be, if you're really concerned about a particular application, then let's model that. Let's actually make a module, take it to a laboratory, and let's test it. And that's also allowable under every code. Every code says if you can show by test methods or otherwise, then that's also acceptable. So, again, we just have to step back a little bit and say, okay, what's the code really trying to say? All the code wants, and all we all want, is safe buildings. And so the code is the conservative model that we always go to. So we're allowed to do other things. Otherwise, there would be no innovation. So we just got to take the rules, and we take the good scientific engineering processes that our industry and our peers accept. And we say, okay, these are our calculations. This is the software. This is the analysis we've done. This is the testing we've done. And therefore, we think it's a fine engineered solution.
Nice.
And that's what we need to do. And it's this day and age with all the software assistance we have, it's not that much more difficult. It just needs a little bit of willpower from the client, the developer, and the builders. And what we've got to do is sell them and show them that we can build better quality, quicker construction, more durable, recyclable, and better for the environment and better for all of us. But we need to spend a bit more time at the front end getting the design and the processes right, and then adopting that to manufacturing processes rather than traditional on-site processes.
Nice. And now the most important question is about cost. So what about cost in comparison to conventional RCC construction? Also tell us about the critical mass, that is minimum number of units required to make project economically viable.
Very good question, and it does vary from country to country. Obviously, the threshold for viability in Australia is a lot less because our costs, our on-site costs, are a lot more, and our time costs are a lot higher than what they are perhaps in India. In fact, if you look at the matrix of labour and materials, it's almost exactly reversed from our country to your country, and that's why we go towards more technology-driven. For us, the number one issue is time. Okay. So yes, there is a capital investment in any factory, in any manufacturing process that has to be paid at the front end. And that's the hardest part for everybody to absorb. Why should I pay? Why should I pay for the factory? And so my answer to this is when we bought the first mobile phone, it was $5,000 US because there wasn't the infrastructure around to cope with that technology. Our first television sets were very expensive. Our first refrigerators were very expensive.
Yes.
Any technology has a lead-in period where the development at the front end it takes capital and it takes investment. So what I have been trying to say to my partners in India is that we cannot look at this as a single project. It's got to be a 5-year business plan where we educate the designers and educate our clients to say, okay, what's the perfect size room? And let's build factory-based environment to manufacture those room sizes. And the same room can be a bedroom and an ensuite and a living room and a study and a second bedroom. It can be the same sized element. It's just how the designers put them together to make them interesting. And then what you'll get is you will get efficiency in manufacturing because you have standardization. And all manufacturing is about standardization. It's a famous quote from the early Henry Ford. He said, "You can have any color as long as it's black." He wanted everything to be standardized to bring the cost of the car down. So what we say to people is you can have size A, size B, and size C, but you can't have size A plus a bit. And you can't have size C minus a bit. Let's standardize these sizes. Let's invest in the molds and the infrastructure. And then, yes, after year 2, after year 3, our amortization of our upfront costs will come down. Our prices will get lower because technically we'll use less steel, we'll use less concrete, we'll use less labor, and our speed of construction, so our funding costs will come down. And if we make it really good for our electricians and for our plumbers and our other tradespeople, the walls are straight, the conduits are already cast in, the penetrations for the plumber are already done. So you should start to see cost savings come from the entire building process and not just the structure. And so if we do our job right and we get this right, then every single other trade on a construction site touches our product. The roofer needs to connect to the structure. The plumber needs holes and penetrations. The electrician, the painter needs to paint our product. The tiler needs to tile on our product. The window manufacturer needs to put windows into openings that we prepare for them. So if we can guarantee the window manufacturer that penetration opening will be plus or minus 3 millimeters, 2 millimeters, and you can make all of your windows with no hesitation that the sizes is going to be right, and the rest is on us, then he can standardize and he can set up and he can manufacture quickly, and the flow on effect for every single other trade will be there. So that's where over a period of time, the costs will and have to come down because that quality and that flow on effect, but to try and say you'll get that all back on your first project day one, I have to see the results now, it's probably not going to happen. And look, every other industry, every other new technology, when you first bought your first Apple computer, it was very, very expensive.
Yes, very nice. Nicely answered. Now, I think the last 3 questions I will ask on manufacturing of these modules, their transportation and assembly. So my first question is for the benefit of listeners, how do we manufacture these 3D models? If you can tell something about that. How do we manufacture these models?
The modules?
Yes.
Look, it's actually pretty simple. I mean, a modular element consists of concrete and steel and labor, and really what we do is we have a sophisticated mold that opens hydraulically and automatically. You push a button, it opens and it reduces. So then the mold is prepared and cleaned, and the window and door openings are placed. The electrical conduits, we have a shop drawing for each and every module that we produce, and so, those elements are placed on the mold. We then drop the reinforcement cage. The reinforcement cage is made independently as a monolithic unit, and that comes across and that's dropped in position inside the mold. Once all the elements are on, we push a button, the mold closes, we tighten some bolts, we close it all up, we pour concrete, we then highly vibrate it and make sure the compaction and the vibration is correct. And then we turn the heaters on and we heat the element up. So we're heat curing it overnight. And then the following morning we come and we reverse that process, extract it from the mold, remove it from the oven, and clean the mold and start again. So it's just a daily cycle. It's a 24-hour cycle. So we're pouring concrete roughly 2 p.m. in the afternoon, and we would be extracting the concrete the following morning at, say, 7 a.m. So it sits in the mold for, 16 hours, 15 hours, and it cooks to 50 degrees Celsius, roughly. And what that does, it brings the heat of hydration up. It starts it's an exothermic reaction. Concrete, when it starts to cure, and when concrete goes off, they say it actually emits its own heat, and it needs that initial heat to get going and to react. And so that's what we're trying to do. We're trying to achieve, a 16 to 20 MPa the following morning, and then it's okay to extract and remove. And most precast processes around the world are like that. You make telephone power poles, you make concrete pipes, you make culverts. All of those elements are a daily cycle, if not twice a day, if not even 3 times a day. And so we use a wet cast, not a dry cast, so that we have at least the best surface finish we can possibly get. So that's the manufacturing technique. And we have big cranes and big equipment to move them. The modules once produced weigh anything from 14 to 18 ton, depending on the thickness of the roof, the thickness of the walls, and how many penetrations and openings in them. So usually we put 1 per truck to transport to site. And we have a series of bearers and a series of transport frames that we deliver them on.
Yeah. I think you have answered this. What kind of equipment, machinery required for manufacturing these models?
So we have a patented mold system. So the mold is the key. The mold is what makes it all work on a daily cycle and automatically. So that mold system is the giant cake tin that we cook from. And that's the biggest cost element. And that is... again, it's just an integral part of the process you can't get away from. Then we need big cranes and big equipment. So we usually use gantry cranes and sometimes mobile cranes, but a gantry crane is the best because obviously you get control and you get safety. But again, that requires some infrastructure. But a gantry crane can work 24 hours a day. So that's the best and most efficient way to do things. So they're the 2 main elements. And then, whatever else is required to pour concrete, sometimes we use pumps, sometimes we use skips. And then it's just all the normal concrete handling equipment, machinery that you use.
Okay, thank you. How do you take care of handling stresses while transporting and hoisting the modules?
There's more stresses in handling and transport than there is in its in-service position. So if you can remove the mold from a module from the mold and store it in your yard and load it on a truck and transport it to site, it's the most stress it will undertake in its life. So that's a very important process and very, very important part. And what I always say to people, look, all concrete cracks. It's all floors, all concrete cracks. And it's just a matter of how small or how big and whether that's a structural crack or not. So my rule of thumb is if it can get to site safely and it's into its position and be lifted up and placed in position, then any in-service loading it's going to go through is not going to be as much as what it went through. So we do get some hairline cracks. We do get some movement cracks because of just the sheer dynamics and the size of what we're doing. But generally, they're non-structural and generally they're only cosmetic and or very, very superficial. So look, we cast 4 lifting elements in the top of each module. So if you can imagine a giant Lego block being lifted by 4 centralized lifting points that are calculated to be around the center of gravity. So each and every module that's produced will have a calculation for its center of gravity lift. And we have a series of spreaders and we have a series of chains and shorteners that will then equalize the load across those 4 lifting points every time the element is lifted. So, it is design, it is engineering, and we say, okay, this is the best and safest way we can possibly lift it. So it's top lifted. When it's transported, it'll be transported on 2 frames so that we have, again, 4 loading points on the bottom when it's transported. And generally those 4 loading points are symmetric with the lifting points above it. So we've designated that to be the loading path for transport and installation. When it's installed in position and it's in service position, the bases are fully grouted up so that all the horizontal elements and vertical elements act as a shear wall that shares the load. So the grout bed that it sits on will help the module share the load evenly around its entire perimeter. So again, getting it manufactured, extracted, delivered, and installed in position is by far its worst possible loading configuration that we've experienced.
Okay, so last 2 questions. If the module gets damaged, do we discard the module or can it be repaired?
That's a call for the production and the site engineers. To give you an idea, I have never had a module that I couldn't repair, apart from when I had a truck roll on the way to the site and it completely rolled the truck and the whole module went over with it, and that was then deemed as being a reject. There are many things you can do in construction that can add to the concrete modular strength and its performance, and engineers will look at that each and every element and say, just have to do this. Maybe it's a plate, maybe it's extra reinforcement, maybe it's a splice beam, maybe it's just patching and filling holes and etc. Maybe some epoxy injection. Anything that you can do with a normal concrete element, we can do with our modules as well. But again, once it's in service position and it's grouted in position, very, very, very slim chance of it moving or deteriorating further. And the site engineer, the production engineer, will look at each and every case and make their determination based on how big the building is, how high it is, what it's going to be used for, etc. All those things. But to give you an idea, I've never had a module in all of my production in 4 different countries that we couldn't use, rectify, modify, or fix some way, shape, or form. So we have very little wastage.
So we come to the last question now. What special traits, skills one has to learn in order to implement the technology in the field?
Probably the most important is just an interest. Like anything, it's a bit different. It's hard to get some people motivated for anything. But look, it always helps if you have a team that's interested in what they're doing. It is a little bit riskier than conventional construction because the loads are big and the elements are big, and the chance of severe damage and or injury is high, but very, very seldom. If you follow the processes and you follow the manufacturing guidelines and a QA/QC manual is followed, then we have very, very, very few incidences, mainly because a module, once it's manufactured and placed on the ground, is very stable. It can't fall over. It's a box. So once it's out of the mold and on ground, or being repaired or patched or painted or whatever, you're not relying on bolts, you're not relying on brackets, props, you're not relying on a suspended slab being supported properly because it's all inherently cast monolithically. So, a lot of those conventional safety issues go away, and it is a lot safer. The biggest risk is in the lifting initially and the transport and the final lifting in position. That's where our risky elements are. Nothing else is risky, and there's a lot less risky days on site doing modular construction, because when you're doing conventional construction, you have constantly moving scaffolds, constantly moving formwork, constantly moving buckets and concrete and Besser blocks and block work. They're all heavy elements, and there's many of them moving all over the building. Whereas when you do modular construction, everybody is away We have a QA/QC manual plan that says, right, we're roping off these areas. The crane, no one's allowed near. Only experienced handlers, only experienced riggers and lifting technicians. There's very, very few people around when we install the structure. Once the structure is up, then your lighter trades can go to work. So it's like I said, there's very, very seldom risky days in modular construction, but the risks are still there, definitely. But once we have that structure up, then the site overall should experience much less risky elements, because the heavy elements are all done in a very short space of time and in big elements.
That will be all. I think it has been a very educative, and I also got a lot of deep insights about the technology. Thank you very much, Paul. I am indeed thankful to you for being part of this lively session and respond to the queries so elaborately and passionately. With the support of people like you who have passion to bring cutting edge technologies in the sector, I am pretty sure that very soon 3D volumetric construction will be the technology for future construction in India as well. And we will also become global leaders in the area of innovative construction technologies. So thank you very much, Paul. Thank you very much. With this, I sign off, and will come again with another session on other new technologies with other experts. Thanks a lot. Thank you, Paul.
Just one last comment.
Yeah.
I think a big congratulations to India. I think your thirst for the knowledge and innovation in construction is fantastic, and I haven't seen that level of interest and passion for new construction techniques anywhere. And so congratulations to India and the government of India, because I think you've really put your hand up and said, we want to be involved in this. We want to invite and inquire about innovation and new technologies, and it's a big congratulations.
Thank you, Paul.
Okay, thank you.
See you again.
Goodbye.
Thank you very much. Thank you. Bye.